So next up, we have Dina Bower, who will be presenting Compact Lunar Mineralogy Imager.
Everybody. So I am actually representing a team of scientists from Goddard Space Flight Center and University of Maryland, led by Shahid Aslam. And I wanted to point out that at the time we submitted the abstract, our acronym was slightly different than now. We're constantly evolving the concept. So in future presentations, you will probably see it spelled with an E for Explorer, because we feel that CLuMI actually achieves more than just imaging, as I will show you. Next slide. So just a quick instrument summary. It's a small size, weight, and power instrument. It's designed to identify and characterize water ice, hydrates, and hydroxyl minerals as well, and as well as other minerals and compounds that are of interest for in situ resource utilization. It utilizes a 1 megapixel SLS detector coupled with an LVF. And on the right, you see this is an image of the prototype. It's based on the compact thermal imager that was flown on the space station. And so we're actually, it's a heritage instrument. So we're able to achieve a pretty high spatial resolution with about 1 millimeter for maps of water, OH, or as I mentioned, other types of compounds and minerals. And our imaging field of view is around millimeter per pixel with a 2 meter field of view. And we've been able to expand the range. We can go anywhere between 1 and 10 meters standoff for our measurements. It does use push broom operations. So it would have to be used on a rover or integrated with a mechanical stepper. So there are a couple of filter options that we are designing this with. So hyperspectral imaging, or a combination of the two, hyperspectral and multispectral imaging. And the great thing is it's a compact and adaptable instrument enough that it could be applicable to different platforms. Next slide. This is a mechanical design of what it actually looks like currently. And so we can achieve hyperspectral imaging between 2.5 to 12.5 microns. And then we also will be able to focus on the water bands and OH bands with the 2.5 to 6.2 micron linear variable filter. And this is just a quick run through of the stats. Okay, thank you.
Okay.
Next slide. So the science that we can achieve, so basically we're looking at mid-wave IR through long-wave IR. So that includes 2 to 12 microns, which covers a wide range of compounds, minerals, as I mentioned. And this includes being able to distinguish between, for example, OH that you would find in ice versus like OH hydrates, which is very important, obviously, to distinguish those. And at the bottom, you see an example of what CLuMI can do. This is from Ito et al. So you're looking basically at a sandy landscape. And through thermal imaging, we can see there are differences actually in surface roughness and the grain coarseness, which will indicate different compositions and obviously processes on the surface. Next slide. So this is just one scenario that we envision. So basically, this is if an astronaut were to deploy this. And so if you could deploy this on a tripod, it could certainly be deployed on a rover in a similar fashion. But basically, it would be set down near a target of interest. And then it utilizes a visible camera to orient the instrument to focus on a target. And then there's a button that triggers the camera to the instrument to start, that an astronaut will trigger. Each frame is actually saved on the instrument and then can be analyzed at the base station or for Earth-based telemetry. And then it does have a reference spectrum library set up so that the instrument will flag specific target compounds and alert the astronaut. Next slide. Next slide. And I just want to acknowledge the Goddard internal R&D funds were used for early instrument development. Thank you.